a ring, but we discussed that moment of inertia is depend on two things. First, mass, and second, mass distribution. That means we need an axis. So for a ring we can take different axes. So if we take different cases above for the different axes. So first we take moment of inertia for a ring about an axis perpendicular to plane. Here the plane is the plane of ring and passing through the center. Here the center is the center of ring. So here we just make the diagram to make it clear. Here it is the ring and this is the center of the ring. We assume the mass of the center is capital M and the radius of this ring is capital R. Then the axis perpendicular to the plane. This ring, in this diagram you can see this ring is the horizontal in the horizontal condition, and the plane of the ring is this when we cut this ring in this from here in the horizontal plane. So this is the plane of the ring and the passing through the center and perpendicular to the plane. So if we assume the plane here, this plane is perpendicular to this. The plane is perpendicular to the ring, a plane of the ring, and passing through the center. So here the axis that we write about, the perpendicular to the plane of the ring and passing through the center. This axis is perpendicular to it and passing through the center. So here this is the axis about which we need to derive the moment of inertia for this ring. For that we need to, this ring is the rigid body, and we discussed that for rigid body we need to take a small component, because the moment of inertia for a rigid body is given as integration dm r square. So in this ring we take a small component here, which is dm, and the distance from center or from this axis dm is capital R. Then we can write I will be integration dm and distance is capital R square. Here if we can take the component in the entire ring and all the component will be a distance capital R. So R is the constant here but dm is the variable. So when we can take the R square out and integrate dm. Dm is the small component of this ring. So when we integrate it dm, that output will be I equals to mr square. mr square. So this is the moment of inertia for a ring about a axis perpendicular to the plane and passing through the center. It's quite easy. We took the small component because it's a rigid body and this component is a distance capital R from this axis. Then we use the formula dmr square. Dm is the small component, R is the distance from the small component, but R for all the components we take on the ring will be same. So we took R out because it's constant and we integrate dm, and the integration of dm is capital M because small m is the component of capital M, and we integrate it, we use all the small mass of all the small components, and that will be capital M. So here is the I, or we can say this I naught or whatever you want to give the name, but this is the moment of inertia for a ring about the axis perpendicular to the plane and passing through the center. Now the second part, we write it here, I equals to mr square for further derivations, and we take it separate and we write different things. Now we derive the moment of inertia for ring about an axis perpendicular to the plane, not perpendicular to the plane. Now this time we take along its diameter. Along its diameter. Here. Now we make this ring. Now this ring is in the plane of this board. Now this ring is in the plane of board. We assume that mass of ring is capital M and radius of ring is capital R. And here this is the axis about we need to derive the formula of moment of inertia. So this axis is along the diameter, that means it's passing through the center. So here for this derivation we use the first theorem, the theorem of perpendicular axis. So for perpendicular axis we need to draw another perpendicular axis. The first axis, then second axis. We can give the name I1. Here the moment of inertia about this axis I2. These two axes are perpendicular, and then we take third axis which is perpendicular to the both of the axes, and that axis will be here. And we can say the moment of inertia about this axis is I, or we can say I naught. Here the moment of inertia is I naught. And so according to perpendicular axis, the moment of inertia of a perpendicular axis to the two perpendicular axes is equal to sum of their moment of inertia. So I naught will be equal to I1 plus I2. And here I1 and I2 are similar. Both are along the diameter. Both are in the plane of the ring. So I1 equals to I2, and we can write I. And so here I1 plus I2 will become 2I naught. So I will equals to I naught by 2, which is equals to, when we put the value of I naught, mr squared, then I, or we can say moment of inertia for a ring about an axis passing along the diameter is given as mr squared by 2. That means the moment of inertia along the diameter is the half of moment of inertia to the main axis, yeah, or we can say the previous axis. So this is the formula for I1 and I2, and that is mr squared by 2, or the moment of inertia passing through the center and along the diameter. So that's how we use the second formula. Now we will derive the formula for the moment of inertia for a ring about an axis along its tangent. About its tangent. Here this is the ring. Assume the mass capital M and radius capital R, and this is the axis along the tangent where we need to derive the formula of moment of inertia. Formula of moment of inertia. So for this derivation we will use the theorem of parallel axis. According to parallel axis, we need a parallel axis, and we should know the moment of inertia about that axis. So here this is the axis along the diameter, and moment of inertia about it is mr squared by 2. We know moment of inertia about this axis along the diameter, and this is axis along the tangent, and both of the axes are parallel to each other, and the distance between the axes are this capital R. So we can use parallel axis theorem, and parallel axis theorem say that moment of inertia of a axis is I naught plus mass and distance between two parallel axes. So here this is the axis about which we need to find out the moment of inertia I. The I naught, that means moment of inertia about main axis, that is mr squared by 2 plus mass of the ring. capital M, and distance between two parallel axes R, capital R, and x square. We add them, then I will become half and 1 will be 3 by 2 m r square. So moment of inertia for a ring about an axis along its tangent is 3 by 2 m r square. This is third case, and now we'll take last case, and after that we wind up today's video because its length is going too long. And for the last case, the case number 4, the moment of inertia for the ring about an axis along its perpendicular tangent, perpendicular tangent. So here we saw the tangent is along the axis, but perpendicular tangent is just an axis perpendicular to the axis along the tangent. We can cite, for that we need to draw the different diagram. We need to use the 3D picture of ring. In the 3D picture of ring, here, this is the ring in this perpendicular to the plane of this board, in this case here, and here this is the axis. Here this is the axis, this is the axis, this axis is passing through the plane, this axis is passing through is perpendicular to the plane and it's along the tangent. So we call this axis along the perpendicular tangent, or we can say just perpendicular to the tangent of the ring. So for this axis we also use the second theorem, the theorem of parallel axis, in which we need a moment of inertia about an axis which is parallel to this axis. So here we draw this axis that we said I naught initially, which was mr square. I naught mr square. This axis is perpendicular to this axis. Here we need to find out the moment of inertia, and the distance between two perpendicular axes is capital R. And we assume that mass of this ring capital M and radius of this ring is capital R. Then according to parallel axis theorem, we know that I equals to I naught plus m d square. Here we need to find out the I, and I naught we know that mr square, the main axis moment of inertia about main axis, and the mass of ring is capital M. The distance between two parallel axes is capital R square. So here the moment of inertia about an axis along its perpendicular tangent is 2mr square. 2mr square. So here we derived today the four formulas for moment of inertia for a ring about different axes. In the first case, we took the main axis which was perpendicular to the plane and passing through the center. The moment of inertia about its axis is mr square. And the last case, the moment of inertia about the perpendicular tangent, which is 2mr square. And along these two axes we derived also two formulas. A moment of inertia about an axis along the diameter, that was mr square by 2, and one more moment of inertia about an axis along the tangent, that was 3 by 2 mr square. These four formulas we derived today, and please if you have notes, then it's okay, you revise it. If you don't have notes of this topic, then make the notes. Whenever the classes will start again, I'll check this. And please stay safe, stay at home, and take care, and be patient, and don't panic, and be safe.